All right, welcome back. We are Game 3001 in the winter 2021 semester at George Brown, and it's week two, part one of our broadcast. This week we're going to start talking about steering behaviors, and I wanted to welcome you back to week two. I know it's been a bit of an adjustment to go from Blackboard Collaborate Ultra to Zoom for some of you. Again, as I mentioned last time, I don't think there is a perfect a tool that we can use for teaching. I use Zoom for to host sessions, and some of you may feel like, hey, how come Zoom? I find that Zoom is, again, more stable than Blackboard Collaborate Ultra. I find that sometimes we drop out a little bit more with that tool as opposed to this tool, and that's why I use it. So we're sitting at week two. We're sitting at week two, which is the week of starting January 19th for us, because we start our classes on Tuesdays, and we go from, where you're doing steering behaviors this week. I handed you assignment one last week. I had a couple of emails that came my way, and I want to address them during lab. But assignment one is something that is fairly basic. It's something that you have been asked to do as a setup, and I'm just going to review that one more time, just to make sure that you guys are all up on board with this one. So again, assignment one, it's due Sunday, January 31st at midnight. Okay, that's the first thing. Under users and groups, you can see that there are no groups that have been created because this assignment one, if I'm not wrong, is individual, I'm pretty sure. So let me take a look here, and I want to make sure that that's true because I don't want to lie to you and tell you it's individual when it's not. Just want to make sure that we've done things right here today. And it's been a while since we keep on updating our CSI and stuff. I'm pretty sure that assignment one is individual though. And just bear with me while we look at that. Yeah. So, and then you're able to work with somebody else on assignment 3 and 4 because 3 and 4 is more difficult. Hassan, I know you asked me that. Video quality looks better. Do we have a quiz this week in our labs? Not for me. Typically what I do is for labs, let me just bring up again the CSI for a second. So here's what it looks like, right? The CSI for our requirements, right? So labs, you're going to get rated on the best 8 out of 10 labs that we do together, right? So every time we do a lab in class, and there'll be several, then you'll get a chance to submit. And normally what it says weeks 2 to 6 and weeks 10 to 14 are when we have labs. You'll also have your midterm test and your final test that are worth 15%, but there are no necessarily quizzes. Labs, basically what you do in lab is I create a lab assignment, and then what you do is if you follow me and you submit your lab up on GitHub, and what I'm going to ask you to do today is I'm going to ask you to take a snapshot of your files to show me what you're doing, then that would be good enough, right? So your lab is basically a follow along, like code along with me. It's kind of a way of doing your homework so that way you're up to date with what we're doing. It's pretty straightforward. All right, so that is what we talked about last week. It's like where your stuff is coming from. And I went through all the different details here. Notice that lab 1 is slated to be happening today. All right, so that's kind of one thing we're doing, but we're not doing a quiz. We're just doing if there's going to be a lab every single week, except for the midterm test week, because that doesn't make any sense for there to be a lab during that week when you're going to have a midterm test. Okay. Also note that for midterm tests, there is no lectures during week 7. Right? I'm going to give you that week. I'm going to be present during that week for labs and lectures in order for me to do a couple things to help you with any issues you might have. So I'll make myself available. but there won't be a formal lecture on week 7. Will the lab be due by midnight? No. When I do the lab with you guys, to give you guys a chance, thank you, Neil, for that. Because different people have labs at different times. For example, the lab that Alex is hosting on Fridays, as an example, well, they get it on Friday, so that's when I'll make it due. I'll make it due Friday at midnight. But for you guys are going to have a couple of days to get it done. So it'll be, your labs will all be due Friday at midnight. Now Alex may change that. He might give an extra day to some of the other people in the class. Can't change name on Zoom. Sorry, I'll make that available. You can change your name now. Thank you. Assignment 1 does not show on the activity stream of Blackboard. Let's take a look at that. Thank you for that. So assignments, and let me see if I edit. Why is that? It should show individual assignment. It should show up. Let me see if that's not display after 1:12 at 10 a.m. and display until February 3rd, January 12th. It should be visible to you guys. Is everyone else not seeing it? Because it should be available to you guys to see right now. Okay, Patrick says he's seeing it. So you should be able to see it. It should be under assignments. I'm not sure why, Esper, but you should be able to see it under assignments. There's the lab, there's the assignment details. And if you open up the assignment itself, and I'll open up that assignment with you. Let's look at assignment 1 together one more time. I went through the assignment details last time. It's not this one. That's for another class. It is this one. And it's due week 3, Sunday, January 31st by midnight, like I said. And like it says here, you will work individually for this one. So this is where you will be working on your own. A couple of reasons why we made this, Alex and I thought about making this individual, is because you need to be up to speed with the framework, which is what I kind of showed you last week to get you going. That's part of it. And also, it's going to help you with your midterm test. That's why we made this kind of individual. Okay, so please follow through with the mandatory criteria in the project setup. I've put together the videos. The videos are up online on how to make this all work. So if you look up on the labs area, in lab 1 where it says Tom, I'm not sure that if Alex is going to have his own videos or not, but I have this lab 1 video that I kind of produced last week for part 2, and it talks about the SDL engine. So for those people who haven't had a chance to look at this, please take a look at these videos that I posted. I posted 2 so far, and I'm posting another one right now. So there's a video in the lecture. So that was 2 lecture videos from last week. One of them was the course intro and intro to AI, and the other one was the assignment 1 details that I went into at some length. So there's 3 videos. So there's 2 videos from the lecture and 1 video from the lab, all posted last week. If you have any questions, please make sure you go through these videos and then ask me that or connect with me on Discord. I know some people have asked some questions kind of ahead of time, but again, remember that please see the videos first. They'll probably detail most of the questions that you might have before you connect with me. All right, we have about 73 people out of possible 80 something. So we're kind of a little bit more close to where we want to be. This is good attendance. Thank you for attending today. I appreciate that. There's some important stuff that we're going to detail today. And so that's why it's important that you guys attend every single lecture and lab. Okay. So again, we're sitting at steering behaviors next week. Remember, assignment 1 is due, and we're going to continue talking about steering behaviors and collision avoidance next week, which is going to help you with your assignment number 1. All right. So we know, here's the lecture. We know that movement is a critical part of AI in games. We know that. In fact, what we want to do is we want to use this same kind of structure. Again, here's a diagram of how this works. We have some kind of interface or input, and the input connects with your AI agent, and the AI agent responds to the input, and then they move appropriately a lot of times. Okay, so when it comes to movement, we want to use some kind of algorithm to move your AI agent around. We're not talking, when we say movement, I'm not talking about character movement as in your movement, your player movement. I'm talking about your autonomous character when they're moving around. So something that's moving around on its own. All right. So again, it's fairly straightforward, the type of movement that we'll use. And the way it works is that we know a couple things. We know that every character has some kind of current position, some other characteristics, potentially velocity, acceleration, maneuverability, mass, and so on. And I've given you that information. I kind of added those different components, if you will, inside of our framework that we're doing together, the SDL engine that I've kind of shared with you. All right, so that's kind of the way it works. And so what ends up happening is we have a structure for our movement for autonomous agents where we have some kind of movement request. The character has to move somehow. And then we go through some kind of movement algorithm, and then we may or may not apply a forces if we want to use force-based movement, so more like physics. Or we just might just change the position. We might use positional-based movement. But either way, we go through a movement algorithm, and then it ends up changing the way that the player or the autonomous character moves. All right, so that's what we're talking about. Movement for autonomous characters in our game, or AI agents, if you will. Okay. One thing to note is we're working in a 2D space in our with our SDL engine, right? So again, we have X and Y coordinates. Sometimes we have X and Z coordinates, depending on the game engine that we're using. Most games, again, are three-dimensional still, and they use X, Y, and Z when it comes to movement. This is kind of a review of what we talked about in your game fundamentals course in terms of our coordinate system, right? So the way we normally work is we orient ourselves to something that looks like this, where we move and we kind of turn in some kind of a number of degrees, as an example, around. Now, computers love radians. So anytime we plug in a formula where I want to turn, especially Euler rotations, Euler with a U, an EU, then what we want to do is we want to convert degrees to radians to pass it into our functions. So for example, I want to do a rotation. I want to do some kind of, maybe I want to, change the, my units. And if I don't change my units, this is what leads to some errors, I would say, inside of our, in our code. So here's an example. Now, the book author kind of uses an example of static structs. But remember what we did last day. I'm going to bring this up here. So I'm going to bring Visual Studio up. And I'm going to look at our template, which is Lab 1B. It says Lab 1B, and we kind of didn't do anything with Lab 1B. There wasn't something for you to submit from last week. But I wanted to bring this up for you because I think it's best to describe things with code a lot of times as opposed to just describe things with nothing. And now all of you should have had a chance to look at the engine. Again, I'm not sure what your class was like on Friday, so your lab, but Alex should be able to go through this template or something similar on Friday with you. Yes? For people who are with Alex on Fridays, did Alex go through stuff with you guys? Yeah. Oh, yeah, and I'm sure he did. He's very thorough in terms of stuff, and we built this together, so he should have he understands how all this links together just like I do. Okay. So one thing to note is instead of a struct like it says here for position orientation, I didn't just do this. We have components, and this is going to help you. One of them is a transform component, and please we use the component terminology very loosely here. We're not using an entity component system. by any means. What we have here is just a transform. And this transform has three vector 2s. And again, remember we're using the GLM library, so the math library for graphics is what we're using. So whenever you want to create a new vector, as an example, we use a vector 2. So this is a vector 2. In our coordinate space, one thing to note is, I'm just going to draw this out here, for SDL engine and for anything that we do together, right? So here's, let's say, our screen. Remember that our coordinate space starts at the top left corner of the screen. So this is, up here is where 0, 0 starts, okay? Up here in the top left corner. I kind of made the circles a little bit ugly, but basically that's where it is. It's really right up here is where it starts, okay? So what ends up happening is that we march along this way on the x-axis. This is positive x starting from here. And one thing to note, and this is a little different than our regular coordinate system for math, we march down positive, when I want to move positive y, that actually goes down the screen this way, all right? So that is going to influence where the position of your object is. So for example, some object that looks like this, we're going to march to the right along the x-axis a number of pixels, and then we're going to march down to where this is. So we're going to march again from the origin. This is the origin. Oops, undo. We're going to march to the right. So again, let's just march to the right. Let's say to this point in the middle of the object, right? So we're going to march this way. And I'm going to show you why the middle in a second. You don't have to make it the middle. And some frameworks work with the top left corner, not my framework, just keeping that in mind, please. So then I'm going to march to the middle as an example and down. And I'm not really in the middle the way I drew my arrows, but this is the middle. So the object middle for us, which is, I'm just going to take this off, which is here, that is the position of the object. It's not this. This is not where we're looking. We're looking here for the middle of the object. This is the middle, the center. And this idea of the center, how do I know this works like this? And how does it work? It's the way I draw my objects. And the way the objects are drawn, remember in the framework last time, if you look at singletons, there's game and the renderer. And we also have another manager, which is also kind of singletons as well. There's something called the texture manager, which we talked about last week. Here's our texture manager. And if you look at the texture manager, it's also a singleton. And when we draw something, there's the draw function. There is an option whether we want for it to be centered or not. By default, it's false. So it's not centered by default. However, I want to point out that when we draw stuff, especially if I have an object, so if I look at game objects, and if I look at, let's say, the player object or the ship object, let's look at the ship object. You can see in the ship object, when I go to the draw function, so I go to definition for the draw option, right? That you'll see that when I draw, their true is selected. So take a look at that. It says, I'm drawing. What's the friendly name of the object I'm getting from the texture manager? It's called ship. X and Y coordinates of where I want to draw. I want to look in a particular heading. I want to have some kind of alpha transparency, which right now my ship alpha transparency by default is 255, which is fully on. And then, am I centered or not? And it says true. So by default, my object here is centered, right? When I draw it every frame. So keep that in mind whenever you move things around. It doesn't matter whether you're moving an autonomous agent or a character, the agent or autonomous character is centered, the anchor is in the middle of the object. That's important to know. So that's what they talk about here. They talk about having two things that they recommend for AI. One of them is a position, so transform.position, and orientation. I don't have an orientation as part of my struct. I have a position, a rotation, and a scale. Orientation or heading might be something that we produce inside of our object. All right. So we also have something called 2.5D. 2.5D kind of creates a an isometric kind of movement where we also have X, Y, and Z axis. We're not going to handle this in our code this semester. But if you wanted to represent something in 2.5D, you're really using 3D with a different kind of perspective to make it look like it's, kind of you're limiting it to 2D, the camera, but actually what's happening is you're really working with 3D coordinates. Vector orientation. So this is important. So when I'm looking at a particular object, so in trigonometry, as an example, when I want to look in a particular direction, it's usually sine over cosine. All right. We're going to do a little bit of trig in this course, and you can't really do much, even in physics, without the understanding of triangles. Right. And let me go back to that. So example, I want to move my object from this position, let's say over here. So I'm going to draw a vector, right? Let's try that again. I'm going to draw a vector from the middle of where I'm going to where I want it to go. I want to go this way, let's say, right? But even if I draw a vector and I want to go into this direction to another point in space, what's really happening is I'm drawing a triangle. So I've got, one axis of the triangle this way, and I've got another axis of the triangle this way. So I'm using a triangle, and I've got some X component on this side, right? So here's the X component on this side. This is an important note, so how things move, right? And then I've got a Y component on the other side. So some Y component, right, that I'm updating on the other side. So here's the Y component, right? Which gives me basically, if I reduce my vector into X and Y components, I get a number of pixels that I'm going to march to the right, let's say in this case, and a number of pixels I'm going to march back up. And when I march up, if I was going to do that, just as we talked about earlier, remember that when I march up the screen for you guys, that's a negative Y, some kind of negative Y that I want to do, because marching up the screen is negative, marching down the screen is positive. Keep that in mind, that things are flipped. And it's a little bit counterintuitive in terms of the way we think of math. We would think that this is a positive Y direction, but actually, because of the way things are drawn on the screen, it's a negative. All right, so that's what it talks about. And so then when I want to find the angle between where I want to go, I'm going to get some kind of normalized coordinates that I want to do. And the way to do that is, let's suppose that this is my target. So my target is something that is up here, right? Let's suppose that my target is, if I can draw properly, is there. Let's do that again. And let's make it a circle instead of circular. And let's just draw the thing here. So let's just draw one of these and move it around. Let's suppose that this is my target. So my target is up there, right? Remember that my target is not the edge of the circle, but rather that it is, if this is where I want my character to move, I start my character here and I want to move over here, right? Remember that how things function, right? That the middle of the circle is really the target, not the edge of the circle. So my vector in effect, it doesn't look like this. Just make sure that that is the case again. I want to see if I can draw this thing properly. There we go. In effect, the vector is like this. Okay, that's what it looks like when I draw my circle from this part to this part, I'm moving this vector this way. And the way to get the direction, the circle's anchor's in the middle, yes. If I want to get the direction that this circle is, like what's the direction that I gotta look or go to when I go to the circle? I'm gonna take the location of the circle. So here's the formula that I'm gonna use, all right? So I'm gonna say, what's the location of, or we'll call it position. So the transform dot position of the circle, right? We're going to take that information, right? And then I'm going to subtract, right? I'm going to subtract the subtract symbol. I'm going to subtract the transform position of my square or my rectangle, let's say. Transform dot position of the rectangle, right? Whatever that is. But if I was to do that, if I was to take, let's say we had some numbers, let's put some numbers here as an example to play with these numbers. And I'm talking about this so you understand the challenges that are involved. Let's suppose that the circle's position, let's start with the rectangle. So the rectangle looks like it's going to be somewhere halfway through the screen, let's say at something like 400, right? Because let's say the screen is 800 pixels wide. Let's just do some kind of scale for you guys to understand this. So here's the screen being 800 pixels wide. And from a height perspective, right, let's suppose that the height of this thing is 600 pixels, which is what I have by default carved out for you guys. All right, so this is the height. So 600, 800 by 600, right, let's suppose. That means that we're about 400 pixels in, and somewhere in the middle of our screen, somewhere around 300 pixels. So let's suppose that the position of our rect is at 400 and 300. Okay, I'm positioning this on for you so we can see it. So that's what this is. 400 and 300 is the position of the rect. And let's suppose that we kind of do the same thing. So we'll say that this is about 3/4 of the way. So let's say this is at 600, and this is about 1/4 of the way up. So instead of it being 300, it's about 150. So let's say it's 600 by 150. All right, let's do that. So again, 600 by 150 is the position of the circle. All right. If I do vector subtraction, if I subtract this from this to get the direction, what I'm actually going to get is a large number, right? I'm going to get this vector, the whole magnitude of the vector here, right? So let's do the subtraction. So I'm going to let's do that. So we're going to say that 600 minus 400, just regular vector subtraction, is 200. And okay, now here's something. So 150 minus 300, and there's the thing, there's the rub, it's a minus 150 that we're going to get. That's the new vector. The vector is going to be 200 minus 150. That's why it's going up in the negative direction. Yes? This 200 minus 150 is the entire length. We don't want the entire length. We want normalized coordinates. Normalized coordinates. We want the direction that this is going in. All right. So we want to normalize this this vector so that it is some portion of 1. Some portion of 1. Right. How would I normalize this? What do you recommend? Right. So how do I do that? So how do I take, as an example, this 200, 150 and come up with some kind of ratio for normalizing the coordinate frame? Does anyone know how to do that? When I mean normalizing, I mean I want it out of 1, right? So it's going to be from 0 to 1. And we're going to see some very nice numbers. There's going to be some common numbers we see in when we deal with AI. One of the numbers is from 0 to 1. Okay, that's the number range we're going to see. So that's a very common number range. Okay, 0 to 1. The other number range we're going to see a lot is -1 to 1. Okay, that's the other number range we're going to see a lot. Okay, -1 to 1. All right, so how does 0 to 1 work? Let's suppose that I want to talk about color. A color, right, before we get into this, a color can be, as an example, 0 to 255 for each of the channels, right? So let's say, for example, red could be 0 to 255, right? If 0 to 255, that's another range you might see, 0 to 255, right? Where 255 is all on and 0 is all off. Okay, you're going to see this color range, right? If I want to normalize the color range to make it to remap it from 0 to 255, I want to remap it to 0 to 1. What do I need to do? How do I remap it from 0 to 255? Right. Well, whatever the color number is, then divide it by 255. Right. So, for example, let's suppose that I had a value of 255. Well, that would just be 1. So that's fully on. Right. And if I had something that was 50% color, so 128, again, if I take a look at that, it would be 128 divided by 255, which is equal to 0.5, approximately, right? So that is how we would map or remap, normalize our color values. Instead of going from 0 to 255, we're going to go from 0 to 1, okay? 0 to 1 normalization is what we're calling this. This normalization that we do is much easier for us to deal with because once we start normalizing stuff, we can start using the 0 to 1 range to come up with a percentage. So 0.5 actually means 50%, right? 128 divided by 255. So how do I normalize this? What do you think I can do to normalize those values? I want to normalize the value that I'm getting here. So divide by 200. Nope. X divided by Y, divide by the screen size. If you divide by the screen size, you're going to get something else, right? You're going to get an aspect ratio. That's what you're going to get, right? Which we don't want to exactly do. Not exactly this. We definitely want to divide by something. So what do we divide by? Because we want to normalize. Normalization means we divide by something, right? So what about the magnitude? So how do I find the magnitude of a vector? Remember, a vector has both magnitude and direction, right? And by the way, I'm bringing this up because you're going to have to figure this out, right? So magnitude and direction, that's what a vector has. So vector, right, has both magnitude and direction, okay? That's what it has, magnitude and direction. That's the property of a vector, right? Pythagorean theorem, yep, we can do that. Magnitude is just the length formula, absolutely. What's the length formula? It's c squared is equal to a squared plus b squared, yeah? Which means that c, the magnitude, or the distance, if you will, the Pythagorean distance is equal to the square root, right, of a squared plus b squared. That's what it is, right? A squared plus b squared. So we're going to get some magnitude that way. So a squared, so a times a, let's say, and then plus b times b. Okay, that's what c is going to be. That's going to give us the magnitude, or the length, if you will, right? That's what the magnitude is, which is really the distance between these two things, right? So what I want is whatever these numbers are, the total number, I want to say that if I want to normalize these numbers, then we need to take the magnitude. So can someone figure out the magnitude between 600, 150, and 400, 300? What's the magnitude? Can anyone figure that out for me? Well, let's do it together if we're going to bring up a calculator, right? Because we're going to do these things all the time. Magnitude is going to be our friend, right? Again, I'm just calculating this manually for us to get today. So again, I'm going to say that a times a, right? So again, what is a, right? Well, it's the difference in x's minus the difference in y's, right? Is what we want to come up with the magnitude. That's what we want for a and b, right? So 250 is the magnitude. Are you sure? Square root of 200 and square root of 850. Yeah, let's do it this way, okay? So if I want to take the difference in x's, the first thing I want to do is I want to say, what's the initial x? The initial x is 400, and I'm going to subtract 600, and I'm going to square it, right? Which is 200 squared, right? So 200 times 200. So that's 40,000. Let's keep that in. So I'll do a memory plus for that. I'm going to go slow here, okay? And then negative 150 is the total. Negative 150 times negative 150, we wipe out the negative sign. So it's like saying 150 times 150, right? Which is 22,500. And we're going to memory plus it, right? So now if you memory recall, we have 62,500, right? 62,500. And I want to take the square root of that. So square root is 2 to the x, square root. So again, if I memory recall and I take the square root of that, I'm going to get 250. That's how it's correct. Okay, great. That is the magnitude, so the distance between this and this. We need to know the distance in order for us to do something. So if we take that 250 now, and if I say I want to normalize these coordinates, the length, right, to get the direction, then I can say something like the normalized coordinates are 200 divided by 250, right? Minus 150 divided by 250, all right? which works out to be, let's bring up that calculator again, right? So 200 divided by 250 is 0.8. So 0.8. And then the normalized coordinate for minus 150 over 250 is, let's bring up that calculator again, right? So 150 minus, right, divided by 250, right? It works out to be negative 0.6, negative 0.6. And my friends, that is the direction that we're looking at. So whenever we want to find the direction, that is the normalized direction. We don't care about the whole magnitude, because then I would be drawing a line, let's say from the rectangle all the way to the circle. I don't want to draw a line. I just want to draw a little, kind of a direction of where I'm looking. That is where I'm looking in negative point, in 0.8, negative 0.6. Once I have the normalized direction, then I can do a lot with that, okay? Once I have the normalized direction, right? Because then I can multiply that normalized direction, or the direction that I'm looking, by a velocity. If I multiply it by a velocity every frame, I'm going to march along this line. That's what I'm going to do. I'm going to march along this line every frame, right? So example, if I said, let's say my velocity was 10, a strict velocity, a speed, let's say, okay? And remember what the velocity is the number of pixels traversed over frames, right? So number of pixels over frames. So if I said I'm going to travel 10 pixels per frame, 10 pixels per frame, okay? So then I take my 10 multiplied by 0.8. So the first frame that I'm going to move, first place I'm going to move is 10 times 0.8, which is 8 pixels. I'm going to move 8 pixels to the right for the first frame, and then negative 0.6. So 10 times a negative 0.6, which is a negative 6 pixels up. And it's going to keep doing that. It's going to keep doing that over and over again, right? Over and over. Yes, we're going to use floats the entire time. Because the thing is, with floats, we keep track of some precision. And then what happens is with, we can certainly use integers as well. All that's going to do is we're going to lose a little bit of precision when it comes to motion. And sometimes our motion is going to be slightly blockier. For example, it might jump to the next pixel. So you might have, a slightly different alignment of pixels. It's going to be almost negligible in terms of what you see. But we use floats because take a look at these numbers. This is 0.8 and negative 0.6. How can I use an integer here? I'm going to lose my precision. I can't do that, right? So I want to keep it at least floating point precision. It's going to work out to pixels, whole pixels anyway afterwards, right? But we need to have at least this, right? Because we're going to use normalized coordinates for this, right? Or normalized direction, at least. Okay, going back to this. So that's the first thing. So the first thing was we're going to get some kind of value. And notice that these values are in normalized, coordinates. Some x and some y coordinate. That's going to give us a direction. Once I have my x and y direction in some kind of normalized form, I can do something with it. I can do something with it, right? So again, anytime I want a direction, anytime I want the direction to any pixel on the game board, this is a key learning, guys. Key learning is I want to take the final position minus the initial position. Final minus initial. I'm going to get some kind of pixels, some kind of new vector, 200, 150. And then I want to normalize this by dividing it by the magnitude. Once I've divided by the magnitude, I'm going to get this normalized direction. The normalized direction can be multiplied by velocity to give me the direction that I'm moving. Okay, makes sense? All right, so that is the way it works. So it's pretty straightforward, but it's a simple trick, is what I would say, from a calculation perspective. When we talk about kinematics, there's two types of kinematics, right, that we're going to be talking about. Very simple movement is what we're talking about. We create movement algorithms to calculate a target velocity based on the position and orientation. Remember, the orientation is the normalized, number that I'm looking at from the where my target is minus my initial position. So final position minus initial position. I'm going to get a magnitude, right, for that, and I'm going to normalize it to get a orientation. That's what the orientation is. So this thing here, orientation, means my normalized direction, if you will. That's what it does, all right? And this will allow the output velocity to change instantly, right? But one thing to note is the velocities in the real world don't change instantly. We accelerate, right? And so sometimes we use some kind of smoothing algorithm to do that. And the smoothing algorithm, as an example, is called usually we use something called a lerping algorithm, or linear interpolation. All right, so here's the next lesson, guys. Linear interpolation. How does this work? Well, I'm gonna erase this now. We're gonna come back to this in a bit, but I'm going to erase it. Okay, I'm gonna make a new thing. So when it comes to linear interpolation, I want you to think about a line segment again. All right, so I want you to think about this. Okay, so let's put my screen back. So here is my screen. We know that this is 800 wide, so the width is 800, right? Okay, here's my width, 800. And again, I'm just using arbitrary values. And here's my height, which is 600, right? In this case, my height is 600, okay? I'm putting it this way because notice the height goes down and the width goes across, right? That's why I'm doing it. And I'm going to draw those lines now, right? So again, I'm just going to use this and I'm going to draw across this way, right? And you can see that here I'm moving across 800 pixels, and then from here I'm going to go down, some 600 pixels down in this direction, right? All right, so 800 by 600. And what I want to find is, I have 2 points, right? So I have a point, and again, let's say if this is halfway in the screen, let's say we're in the middle of our screen again. So this is the middle of the point, and I want to find the direction of another point. I'm going to use some other direction, okay? Some other position. So let's say I have a position somewhere down around here. So this is kind of a different position. So this, we'll label it as P naught. So P0, let's say P naught is also what it's called. And then we also have another one, which is P1. Okay, there's P1. So we want to make a line segment that goes between those 2 points, right? So for example, I want to draw a line segment from this point all the way to this point. Okay. We can say then that 50% across this line segment, 50% across this line segment, right? Somewhere right here, that would be 0.5, right? So if I was to draw a line approximately, let's say right here, and that would be, you would consider this at 0.5. Hear me now. Would you agree? 0.5, the distance between here and here, we're halfway between the distance between here and here. And if we're measuring from P0, I'm measuring from P0 to P1, right? Or from P1 to P0, 0.5 remains the same. Here's where it changes. If I'm saying I'm measuring the distance from P0 to P1, right? And I want 0.1. So 0.1. So 10% of the distance, let's say between 0.0 and 0.5 would be something like kind of over here, let's say. Okay, that's kind of where 0.1 is. And let's draw that with a line. So again, I'll draw a line. Follow me here. I know this is, you're like, so what is he getting at here? You'll see. Let's suppose that this is 0.1. Let's suppose. Okay, it's not really, but I'm just drawing it roughly. So let's suppose I label something that this is 0.1. Okay. So what 0.1 means is it's 10% of the way from P0 to P1. This is 50% of the way from P0 to P1, right? And if I was to draw another point, and again, I'm sure you're seeing this coming, right? Then if I made another line over here, let's say, and let's say I said that that would be 0.9, right? Look at the values I'm using. 0, 1 to 1. 0 to 1 basically is what I'm doing, right? This 0.9, right, is 90% of the way between 0.0 and 0.1 along this line segment, right? 90% of the way. What I'm actually doing is I can linearly interpolate between 0.0 and 0.1, and I can plug in what's called a t-value. These are the t-values. The t-value here is 0.1, the t-value here is 0.5, the t-value here is 0.9, right? So what I'm actually doing is I'm saying, okay, so how do I find 90% of the way, from P1 to P0? Well, I want to find the total magnitude. So I get the magnitude of the line. And let's say, for example, this is also 250, right, from a magnitude perspective. So I know that I want to march across this line 90% of the way across this line every single frame, right? 90% of the magnitude I want to take across this line and get to this point, right? So I take the magnitude minus multiply by 0.9. Thank you very much, Sean. And that's going to give me some value that's closer to P1 than P0. So again, I'm linearly interpolating between this and this, right? I'm doing the same thing. If I want to march the other way from P1 to P0, 0.9 is actually 10% of the way from P1 to P0, right? This is 0.5 for both ways. And this is 90% of the way from P1 to P0, the same idea, right? So this X number of percentage away is the numbers that I'm getting from 0 to 1, okay? The way we linearly interpolate, so we talk about linear interpolation, right? Is some value between 0 and 1. Okay, some value between 0 and 1, the t value. So the t value, which is some value between 0 and 1. Okay, that's what the t value is. So whenever we have a formula for linear interpolation, we're going to have the t value that we want between 0 and 1. Okay, and then we're going to get the initial position and the final position. Now, I've done a lot of the heavy lifting for you guys, right? Remember I talked about this last week. There are some utility functions that you have in your code to help you to do some of this smoothing, the smooth function. Think about this as smooth step if I want to use something. So inside of our core folder, under util, there are a lot of little utilities that I've included. Clamp, and there's also something called lerp. Take a look at that, lerp. From A to B with some kind of t value. Float means for some x value to some other x value, right? I can do that. I can also lerp an angle from some angle A to another angle B across some t value, right? So this is important to note. Okay, so I've given you some utility functions so you don't have to figure this out on your own. Let's take a look at the lerp function and what it looks like. So go to definition, all right? It's pretty simple, right? It says I want to take my b value, whatever the b value is. I want to subtract it from a, and I want to add a to it, and I want to multiply it by a clamped t. So t, remember, you can pass whatever value you want of t. And what clamp 0 to 1 does is it makes sure that t is clamped, it's restricted between 0 and 1. So if I give a value of 2, right, which is impossible, t can't be 2, right, then it's only going to allow you to go a maximum of 1. That's what clamp 0 to 1 do. However, sometimes it's nice that we want to kind of move along a line and not be clamped. So I've also produced a lerp unclamped method. And what this does is it doesn't care what t is. It could be a negative value or less than 0, and it could be a number greater than 0 or greater than 1, and it will still figure out the final floating point value. Okay, all right. So why am I showing you this? Because we want to be able to do some kind of vector2.lerp, right? I want to do a vector2.lerp between the initial position and the final position, okay? So one thing to note is GLM has a lot of really cool functionality. If I go like GLM vec2, and if I go dot, right? How about if I do lerp? You can see that GLM comes with a lerping mechanism where I can pass in any value that's in there, and I can say that I want to pass in some template type. For example, let's say a GLM vec2. I'm just putting it here so you can see how it works. This is not where I would put it, all right? But let's suppose I want to make my own lerping function for 2 vector2s, right? As an example. Then you can see that it takes a vector2 and then some other vector2, right? And then some kind of t value between 0 and 1, let's call it 0.5, right? And what it basically says is this. It says that the lerping function that says linear interpolation of two quaternions, right? The interpolation is oriented, right? X is some quaternion and Y is another quaternion. That's why this doesn't work, right? I want to be able to do something like this for you, right, without us doing using GLM. That's why I haven't used GLM for my lerping algorithm. So let's write a new vector2 lerping algorithm, right? Remember that I'm going to linear interpolate not just on the x-axis, that's the float, but also on the y-axis, right? Yeah, quaternions are coming. So how do I do that? How do I write the function? And I'm doing this with you guys here because linear interpolation is something we're going to do. So I'm going to call util, and I want to call a lerp, but I want to overload the lerping function. All right, let's make a brand new function. So static, it's going to return a GLM vec2, right? And I'm going to call it lerp still, but instead of it taking two floats, it's going to take two vectors, two vec2s, GLM vec2, and we'll call this position 0 and GLM vec2, and we'll call this position 1, and we'll still have a floating point t value. So now what we've done is we've created an overload for the lerp function in our utilities. Again, I'm just doing this on the fly with you guys, right? Help me code this thing, guys. I want to make this new function. So I want to declare this function, right? So one thing we can do is we can use a little arrow here to generate the implementation, little light bulb, generate implementation. Here it is. It's an empty implementation, and I did this with Visual Studio. I want to use lerp, this lerp, right? And I want to return a GLM vec2. So what I'm going to return is a new vector. That's what I'm going to return. Some vector between these two numbers. How do I do that? What do I do? How do I use this thing? Help me code this thing. Well, we know that the difference in x's is what we want. So we'll make float, and we'll say difference in x's, right? The difference in x's is going to be some lerping value between, right, the x initial, which is our p0.x, and p1.x to some t value. All right, so that's going to be the difference in x's, right? And then what I want is a float. The difference in y's is going to be some, and let me not call it difference in y's, but we'll say lerp x's, right? And we'll lerp y's. How about that? It might be different. I know lerp is a weird name, and some people laugh when they hear it. Lerp. There's also something called a slurp, right? Okay, so how about the other way around? X and P1. Oh, no, I was right. P1.y, and then some t value. All right, so that is going to give us the t values, sorry, the position in x and y between the values that I'm getting from P0 to P1. Okay? And then what I want to return is a brand new GLM vec2, right? Which is going to be the lerp x's and lerp y's. Does this make sense? Lerp. I'm linear interpolating between some x and some y value, but I'm doing the x's first because I can only return this one here. This lerping function up here only returns floating point values, a number between x's, right? So I'm actually projecting onto the x-axis with this one, right? And then I want the number between on the number line that I'm giving, the number on the line between P0 and P1, the line segment, right? And I want to get the number between those, and I'm going to do lerp on the y's, whatever that t value is that I get, that 0.1 or 0.5, whatever it is, right? And then I'm going to just sub in those two values and create a new vector that I'm going to return back out. Okay, make sense? Let's do some funky stuff. Notice that there's these little underscore things. Don't ignore these things. These are some suggestions. It says add const. I agree. Add const, because we can make that a little cleaner. Add const, right? So these are the things that it does here. Same thing here. When we look over here, it says some coding. It tells us to code a different way. It says add const and add const because those things aren't going to change. And also, it doesn't like just const. It also says use auto, const auto, because this is a kind of a cleaner way of doing it. Also, lerp x and lerp y, it doesn't like the way I've named it, because the coding style that it's suggesting is suggesting that it should be something that is underscore, using the underscore, lerp x's, and only the stuff up here should be the way it's going to be here. Resharper, yeah. I'm okay with this. I'm going to ignore what it's suggesting here, but this is our new function. And I've only done it here in our on our video here. But again, think about what the power this allows us to do. It allows us to linearly interpolate between some position and another position, right? Once I have this linear interpolation happening, then what I can do is I can calculate the the next position, right, relative to the t-value, some value close to the t-value that I'm going to get to. Okay, and that is the smoothing function that it's talking about. The smoothing function, I can smooth the velocity every frame by saying I want to go 90% of the distance between where I am and where I'm going to go. 90% of the distance. Should we add this to our code framework? I'm going to add it for you guys, Ethan, but yeah, you can certainly add it. This is just a function that we're coming up with here on the fly to help you out. All right. So this smoothing function is what we're doing. Smoothing function. All right. It says that characters need to keep track of their linear and angular velocities, because once I have my velocity, we're going to think more in terms of our linear velocity. Angular velocity is something we're going to calculate in another scenario. But here's an example of our new struct that's called kinematic, and this is from the book. They recommend a position, an orientation, a velocity, and a rotation. We don't use this in terms of the way our framework works. In fact, ours looks a little bit different. Let's take a look. We talked about components, and the other component we have is something called a rigid body, right? So we have a rigid body that has mass, velocity, acceleration, and to calculate, to keep track of if it's colliding or not. State. I'm colliding or I'm not colliding, right? So that's what the rigid body component does as well. And velocity by default, any of these items are defaulted to 0. So for example, if I don't set my velocity, it's 0, 0, and my acceleration is 0, 0. Remember how acceleration works. Acceleration adds to the velocity every frame, right? So it makes it faster and faster or slower and slower, deceleration. All right, so I have rigid body instead. So I have 2 structs, not just one. Here they recommend something called kinematic. I've just broken mine down into a transform, which is position and rotation, as well as a rigid body, which is velocity, right? Orientation is something else, and I haven't added it into either the, that's more like a rotation. If you think about this, right? If I keep track of rotation, and I put my rotation as normalized coordinates between 0 and 1, as I could also put another way of rotating things. I could put in my rotation a number of degrees on the x-axis and the y-axis, as an example. I could do that too, right? But remember how we're rotating when it comes to x and y coordinates. How am I going to rotate on a 2-dimensional screen? Think about this for a second. If I want to rotate this entire thing, across, like around the this anchor point at 0.5, right? I'm actually rotating across the z-axis, right? That's what I'm doing. I'm rotating across the z-axis here, right? So, I mean, I could totally do that. I could rotate around here. But what I'd want to do is I want to talk about the rotation, the number of degrees that I'm going to rotate the line segment. And the way I would rotate the line segment is I would rotate each of the, recalculate each of the x and y coordinates, right, to perform an Euler rotation. I could also use matrix rotations or quaternions to rotate from one position to the other, but that's more complex. All right. So then what they're looking at is steering output. There's 2 kinds of, rotations, a linear and an angular, right? is what they're looking at. And again, they break it down this way. We don't have to do that. We have other structures that we're going to use. But I'm just showing you this so that way, if you look at the books, details, you're like, so ours is very different than Tom's. What it says inside the book, which is where the PowerPoints come from, and what I'm telling you to do is different. Well, but more or less, I've just broken it down differently. One thing to note that the idea of facing, right, is totally different than velocity altogether. If I have velocity means, think about what I'm doing here. So if I want to move an object, right, and I'm just going to draw a new object. So there's difference between, so here's my object, right, there it is, and I want to move it. Okay, so let's suppose, I'm also going to produce, sorry, one before I move it, let me produce an orientation, right? So let's suppose that this line here from the anchor point across, right, this line here is the direction that the autonomous character is pointing. Okay, so I'm pointing in this direction, this ugly arrow I just drew. So let's suppose I'm pointing in this direction, okay? Let's make the arrow a little nicer. How about that? So I'm sorry, it bugs me. Yay, there it is. So I want to then grab this object, right? There it is. And I want to move it. So if I move from here, let's suppose I'm at this position here, and I want to move it from position 0 to position 1. Is this okay? Can I move like this from this position to position 1? Think about this as an example. I move from here. Can I move down here? Is this a position change? Yes or no? Yeah, it's a position change. But here's something. And am I looking where I'm going when I do this from here to here? Am I looking where I'm going? No, that's a different thing. Look where you're going is another algorithm, right? Why? This is just position change. This is just from one position to the other when I come from this position to this position. That's what I'm doing here, right? Orientation, if I was going to change to look where I'm going, I'd have to reposition across the line of incidence. So I'm kind of moving in this direction. That is look where I'm going, right? And I did two things, if you notice. I'm moving, I'm translating my position, as well as rotating my direction or my orientation so that it's looking where I'm going. That's a different thing. And that's what this thing is saying. That's what this thing is saying. So velocity and orientation are independent. They're not something that's related one to the other. Here's an example. Here's frame 1 where I'm smoothing my facing. Here's frame 2. I'm moving closer to where I'm going. Here's frame 3 and frame 4. I'm not going to go from this to frame 4 right away, because if I go from frame 1 to frame 4, it's going to look wacky. Like it's going to look really fast to go from this orientation to this orientation, right? I'm going to smooth over a certain amount of frames, and I'm going to use linear interpolation to do that. So some value, some t value over a number of frames. As my march from one frame to the other, my t value is going to grow from 0 to 1, where 1 is the final orientation and 0 is the initial orientation. Again, we can linearly interpolate from any number to any other number, right? I can go, example, I want to linearly interpolate from 9 to 21, okay? And I want to get the a 0.7, my t-value is going to be 0.7 from 9 to 21. So how do I get that value? Just like we saw in the formula, we're going to say, take 21, subtract 9, right, is equal to 12, right? Okay, that's the total number of units, if you will, right? I'm going to subtract 9, right? So I'm going to start at 3, right? And then I'm going to multiply by some t-value, for example, 0.7, right? And that's 2.1 units away from the final position. I'm going to add that back into, I'm going to subtract it from 21. So 21 minus 2.1, right, is roughly 18.9. And that's 0.7 of the way across from, let's say, 9 to 21. Okay. Again, don't worry about the formula. The formula is inside of our code right here, inside of our util.cpp lerp, right? So b minus a, right? And we want to add, we want to multiply, actually did it wrong. So remember order of operations, do this one first, then multiply by t value. So b minus a, multiply by some value, and then add it back into a. Let's try that again. Sorry. Let's try that again. So again, let's say 9 and 21 are the two values, right? So I take 21 minus 9 is 12, multiply it by the t value, 0.7, and then add it back into 9. And then you get 17.4. That's the actual value. 17.4 is 0.7 away, 70% of the way from A to B, if A was 9 and B was 21, right? So because of this, you can use any two values, right, to linear interpolate. Let's suppose I want to go from an angle like it shows here in the thing. Let's suppose this angle pointing north, let's suppose that is 90 degrees. And let's suppose this angle pointing down this way, right? Let's suppose when we rotate to the left, right, counterclockwise from 0, where it's east, to 180 degrees on the west, 270 on the south, and 0 again, or 360 on the east, right? So this is some in the fourth quadrant over here. Some rotation, we could see it this way, or we can also see it a positive rotation this way. By the way, these really weird rotations that's happening, negative and positive, we're going to run into some of these issues, especially when it comes to this, right? Because it's actually below the equator, below the 0 line, some value. So almost like a negative, let's say some value down here, let's say negative 30 degrees, right? So from 90 to negative 30 is what we're doing. Well, let's plug in those values, right? So we're going to go back to the equation that we had, right? Here's our equation, and we're going to plug in those values. So my initial value is 90, and my final value is negative 30. So I'm going to say 30 negative, right, minus 90, right, minus 120, multiply by the value that I want to go, right? So let's say, for example, I want to go halfway there, 0.5, right, is minus 60 plus the initial value of 90, right, plus 90, right, which looks at 30 degrees. So halfway between negative 90 and negative 30 is 30, right? So that means that if I was going to go back to here, from here to here is something like this. This is like 50%. Make sense? I'm rotating this way. And that's the way we can linearly interpolate or do some kind of smoothing from one direction to the other, right? We're going to use these numbers 0 to 1, negative 1 to 1, linear interpolation with a t value over and over again over the course of the time that we're together this semester. So something that's of a learning for you guys. All right, so updating position and orientation. Again, it gives us a way of doing that. And here, notice it says def update. This is in some kind of pseudocode. And when you look at this, it's like Python, because def is how you define stuff in Python, right? So this is our struct that's kinematic. We have some kind of update method. And look what it does. It says my position plus equals to my velocity multiplied by some kind of time value plus 0.5 multiplied by some linear steering angle, right? Multiplied by time times time, which is really t squared. So it's like my position is initial value p naught p initial, so p initial plus v naught t, v naught times t, plus 1/2 of at squared, where a is the acceleration, my acceleration across the my rotation, right? That's what it is. That's my velocity. And the same thing goes with my rotation. I can use almost the exact same formula. Okay, so this is like my acceleration, linear acceleration over time, and this is my angular acceleration over time. Both those two things. Okay, and the formula that I just used is a classic kinematic motion formula, right? Where I have my initial position. Let's map this out for a second again. So my formula that I'm using is, so P final, right, is equal to P initial, right, plus velocity initial, right, times time. We'll say times time, right, like this. You know, so plus, right, 1/2, so 0.5 times some kind of acceleration times time squared, t squared. That's kind of the standard formula that you're going to see, almost like the standard kinematic formula that you can derive other formula from over and over again. All right, that's grade 12 physics. We're going to get that. You're going to see this again and again during our physics class together in September. Okay. So P final is equal to P initial plus initial velocity times time plus 1/2 of AT squared. And that's how you're going to get this smooth, kind of mapping of motion. Okay. Actually, this gives you a parabola if you use this in 2 dimensions, X and Y, right? All right, so that is the direction that we're using for, we update position and orientation every frame, which we know how to do. And what they do here is they talk about forces. This is from your grade 12 physics, as an example. We know from Newton's second law that force is equal to mass times acceleration, right? And force is not a number of, it's not velocity, it's just a number, as a number that we're going to use to mimic smooth motion. We're going to get more into this. There's actually, Newton's got 3 laws of motion. And just to remind you guys, for people who've never taken physics before, because there might be a chance that you were in school, in high school, and you didn't take physics for whatever reason. And if you didn't, or if you forgot, remember there's 3 laws of motion that Newton talks about, right? One is, the first law of motion is objects at rest tend to stay at rest. Objects in motion tend to stay in motion. So they're going to keep moving until they're stopped, right? The second law of motion is this one. Force is equal to mass times acceleration. What this means is that the amount of force is directly proportional to an object's mass times its acceleration. That's what it means, directly proportional. And the last one is, for every action, there is an equal and opposite reaction. Okay, so that's what the 3 laws of motion are. We're going to use some of those in each one of our assignments to some degree. All right, I'm not going to ask you for collision response too much. We're going to cover that in physics next in September semester, in the fall semester. And this is where, in some sense, maybe physics should come first. Maybe we should get physics first and then do our AI in the 3rd semester. The challenge with that is you won't have any AI in your game that looks any good at all, right? So that's why, we have to make a decision where physics and AI would go. Theoretically, it would be nice to have them in the same semester. We can't do it, right? So that's why we've separated them out. There's a lot of stuff you're doing this semester, and there's a lot of stuff you're doing in the fall semester. So again, what we want to do is use this. That's what kinematic motion is. We use kinematic algorithms to move from one location to the other. A lot of times, if we want to calculate the direction, we use the arctangent to calculate the new direction. Well, why is that? Well, again, we can use the arctangent, or something else that we can use. We can figure out the calculations by using vector math, which is what we did. Final position minus the initial position, and then divide by the magnitude to get normalized values that we're going to march across that particular line, right? Which might be a little easier than using our arctangent, right? Arctangent means I'm going to get some kind of x value, and is semester 3 offered in the summer? I don't believe so. No, I think semester 3 is only offered in fall, right? So that means that's why physics is only available for the fall semester. So we're going to add here, we're taking the arctangent to figure out here they're using x and z for getting the new orientation. We don't need to do this. We can use our formula that I showed you earlier, which is normalized, kind of a normal that we're looking at to find the final position. All right, finally, we're talking about after some kinematics, we're talking now about motion, and we're talking about some kind of steering behaviors. Okay, there's some great articles about steering behaviors out there. I'm going to link to some of those during our lab session. But one of the things that we talk about with steering behaviors is this idea of a seek algorithm. So a seek algorithm is literally just that. It seeks to the position. So a kinematic seek, there's two different types of seeking. One of them is this kinematic seek behavior. And the kinematic seek behavior basically says, okay, I want to go towards that position with the same velocity. So let's show you what during lab, I'll show you what a kinematic seek looks like, but let's take a look and see if we can find something that's online. So if I do a steering behavior, if you look at steering behaviors, spelled the American way, seek, okay? There's going to be some great, resources you can find that show you how to do the kinematic seek and what it looks like. So this is kind of the formula for what it looks to see. I'm seeking towards a particular target, right? And I want to seek across a certain path. Why? Because I'm going to turn smoothly towards that path every frame, right? I can't go from here to here. What I want to do is kind of this smooth step where I'm turning from one kind of direction to the other, right? So this kind of idea, the steering that I'm doing. So steering is not just immediate switching of direction, but switching in different ways. I'm looking for this one thing here, and there's some great stuff here in terms of seeking. So let's see if they have a seek. I think I just looked at that one. I want to share some resources with you, and this is the same article. But there's some great little GIFs that I want to show you, and there's some original articles, white papers that were made for steering behaviors, and this is the one: steering behaviors for autonomous characters. Right? This white paper that's been looked or shared with everybody is a classic. This link right here, red3d.com, and this is steering. And it talks about how we can have some kind of steering behavior, and there's different ones that it shows here, all in one, right? Here it's showing you seeking behavior. So notice that I have my object, and here's the target, and it's going to seek towards that, and it's going to look where you're going, which is one of the things that I've asked you guys to do. A look where you're going algorithm. When as I go towards the target, I'm going to change my direction, and I can't go sideways because that doesn't make any sense. I can't move sideways. Like back to my drawing, if I want to move from this position to this position, but my orientation is this way for my ship or a minion or some kind of other autonomous agent, it doesn't look right. It doesn't look right. Sorry, let me just do one of these again. For me to be able to do something that looks like this doesn't look right if I do this, right? That's like slipping to the right. That's what I'm doing, slipping, right? What looks right is if I turn this way. So what I'm going to do is every frame I'm going to move. So I'm going to move down this way and then turn slightly, and then move down this way and then turn slightly, and then something like that, right? But again, I'm not going to move across this line. That doesn't make any sense. Instead, what I'm going to do even better, which looks nicer, is I'm going to go with the thrust that I have. So I'm looking in this direction. Well, guess what? This frame, I'm going to move forward a little bit, and then I'm going to turn right. And then I'm going to move forward across that direction, right? So I'm going to move forward across that direction, and then I'm going to turn right. And I'm going to move forward across that direction, and then I'm going to turn right. And I'm going to move forward across this direction, and then I'm going to turn right. And depending on how fast I can turn, my turning rate, if you will, I'm going to keep doing that until I reach this. So I'm going to get a bit of an arc happening, right? And that's what happens. So looking where I'm going is the right way to do things. If I just slip from point 0 to point 1, it's not true seeking behavior. All right. So that's what this is showing us here, this little arc. That's the seeking path, right? And here's the desired velocity. the desired velocity, and here's my initial velocity, my current velocity. And I'm going from current to desired. Guess what I'm doing here, guys? Lerping. I'm going to lerp from this velocity. Remember, the velocity is a velocity vector. A velocity vector has a direction and a magnitude. The magnitude is the speed, let's say 10 units, and the direction is the linearly interpolated value between where I am and where I want to be. Right? And that direction change, right? The direction change. So I have to know what my initial direction is. So I'm pointing in a particular direction, and then I want to know where I'm gonna be, where I want to be. I want to be in this direction, right? I want to point over here, right? So for example, let's go back. So I'm over here. Let's say as an example, let's draw this again. So let's suppose I'm here. That's my initial direction. My final direction is this. I'm going to linearly interpolate between this and this, where this is 1 and this is 0. From 0 to 1. That's what I'm doing. It's linearly interpolating, right? And I want to have my t value is going to change over time. So as I'm marching across, right? So again, first frame, I'm there. My t value is going to change. And now my thrust is going to be in the direction that I'm looking every frame, okay? Again, we're just talking about movement here, guys, all right? And that's where you get this little arc. Here's something that's going to happen. As I change my direction, I'm going to overshoot this value, and then I'm going to turn around again and come back the other way, and I'm going to overshoot this value again. And I'm going to turn around and come back again, and I'm overshoot this value again. I'm going to keep overshooting this value over and over again. Why? Because nothing about seeking behavior is telling me about stopping. It didn't say stop when you get there. It just says seek to the point, which means I'm going to keep seeking. And because my value, depending on how large my velocity is, I'm going to keep seeking over and over again, and over and over again, and I'm going to keep passing by this target over and over again, forever. Okay? That's seeking. Fleeing is the opposite of seeking. So if this is the target, then fleeing is going to go this way, the opposite way. Again, I want to go directly opposite of where I want to go. This is my fleeing direction. This is my desired velocity over here. This is my current velocity over here. I'm going to linearly interpolate between where I'm looking and where I want to go every frame. And so it's going to produce this arc as I move away from it. Okay. Questions around seeking behavior. Seeking behavior, they talk about that in this seek. The first steering behavior learning is seek and flee. And by the way, those two behaviors are inside of your assignment number 1. Samuel asks a random question. If you're oriented the complete opposite of the target, what would you determine whether you went clockwise or counterclockwise? That's a good question. So it really determines how your turning algorithm works. Some people always turn to the right. Some people always turn to the left. Some people randomize it. They have a RNG value and they go, okay, so I'm perfectly aligned. So I'm 180 degrees. I could turn either one way or the other and it would make no difference, right? As an example. So roll the dice, which way you want to go. Or always turn to the right or always turn to the left. It really depends on what your algorithm looks like. If you're 100% like 180 degrees opposite of where you want to go, okay? Which is what's going to happen when you pass by your target, right? However, if I've passed by my target and I'm somewhat closer on the right than I am on the left, then I want to move towards the right because it's closer. I want to go in the direction that's the least angle. I want to find the lowest angle to go from the right or the left. If the lowest angle on the right side, turning right or turning left, is equal, randomize it is what my recommendation is. Or you might have another preference. Maybe move always to the right. Right-hand rule. All right, so that's the seeking algorithm that they talk about here is kind of what it looks like. And take a look at what they've done here. They normalize, like I did, the velocity. Once we normalize the velocity, then we multiply it by the maximum speed, and we're going to get into that direction every frame. All right? That's the seeking algorithm. All right, the flee modification is the opposite, the reverse of the steering action. So basically, as I'm moving towards it, I'm going to get the opposite. I'm going to go in the opposite direction of the seeking algorithm. So seeking and fleeing are directly related. Here's something else, arrival. Okay, now this is different. arrival is a little different than just seeking. So what arrival says is, well, as I approach my target, right, I want to start slowing down. So it says we check to see if the character is within the radius. Okay. Let's draw this out. So I want to seek. Seek is just, I'm going to keep going there. And let me just undo that change. If I'm going to draw a line from here, a smooth line from here to here, imagine that I'm going to keep on moving towards the target. And as I move towards the target, I'm going to bypass the target, and then I'm going to turn around again, right? Actually, let's undo that change. Let's do that again. So I'm seeking towards the target. I'm going to go toward the target, and I'm going to keep going in the same direction. And then what's going to happen is I'm going to turn around, right? And I'm going to come back the other way around and seek towards the target again until I find this way. And then depending on my turn rate, I'm going to turn around, or whatever I do, I'm going to keep going. This is seeking behavior. I'm going to keep going this way over and over again until I, get to the target again, over and over again. That's what seeking looks like, right? I'm not going to stop. Arrival doesn't do that. Arrival says that I'm going to come, and as I approach the target, I want to slow down. That's what I want to do. I want to slow down. And the way to adjust for that is what you do is you create a radius. So let's see if I can do this properly. No. You create a radius. No, it's from the middle. So I guess it's like this. I create a radius around the target, right? And what I do is when my object, here's my object, when I draw my object, as I get to the radius, I'm going to keep going around the same speed, but as I get to the radius, I slow down, slow down, and slow down, and slow down, and slow down until I stop. That's arrival. Okay, as soon as I hit that outer radius, some distance away from the target, that radius, I start slowing down and slowing down and slowing down, which means I need to know where I am at. What's the distance from the target every frame, right? Is it like momentum? No, it's more like I'm braking. I come up, I'm velocity, I go to maximum velocity, and as I hit the edge of the radius, I start braking until I stop. Okay, that's arrival. So arrival, right, is different than just seeking. Seeking is just going to find the target and keep going by it and keep going over and over again. But what arrival does is as it approaches the target, right, here's what arrival looks like. So I go, and then as I approach the target, I start slowing down. And notice that there's a radius. This radius is where I start really slowing down more and more and more until I stop. Okay, so that's kind of like arrival. Arrival can be used for everything from seeking to fleeing to pursuit to all kinds of stuff. Arrival. And it's a smooth step. It's a smoother way of arriving at your destination. If I just use seeking, I pass my destination because my velocity is going to stay fixed. Okay, that's what's going to happen. My velocity is going to stay fixed. Okay. All right, so that's what arrival is, and that's what it talks about here, the arrival algorithm. That's how the arrival algorithm works, and it talks about having a radius and the time to the target. Now, kinematic arrive calculates the time that I want to make to the target. So I'm going to pre-calculate how long it takes me to make it there. And I'm going to work it out so that I'm exactly at the target within X number of frames. Okay, that's kinematic arrive. All right. Time to target. Notice that it says some kind of constant that I'm going to give it, right? It's not dynamic. I'm going to give it a value. Okay. That's kinematic arrive. That's the difference between kinematic and dynamic. And we're going to talk about that next week. All right. And then it has the algorithm that we talked about before. Notice that it says my velocity is the target position minus the character position. And this is the magnitude. That's the magnitude of where we're going towards every single frame, right? And it says if my steering velocity the length of my velocity or the magnitude of my velocity is less than the radius, then I want to start to slow down. Okay, that's what we're going to do. Okay, and whatever that radius number is. Okay, and that's how it arrives. Then what you're going to do is you're going to take your steering velocity and divide it by the time to the target, and you're going to keep on slowing it down. That's kinematic arrive. The next one is the wander algorithm. This is great. So what wander does is it has some kind of value in front of it, and we use random numbers to meander, like it says, to the left or to the right. Now, you don't want to do this every frame, otherwise it's going to look really jittery. It's going to like jump around a lot, right? So what you want to do is every X number of frames, you're going to start looking like you're going in a different direction. You're moving to the right, or you're moving to the left, or you're wandering to the right, or you're wandering to the left every frame. Okay, that's what's going to happen. Okay, and what that does, here's the wander algorithm. You're going to basically get some kind of maximum rotation, some kind of maximum speed, and what you want to do is you want to generate a number, some random, like it says, binomial, right? Random number, random vector is what this is. A random vector, okay? And we have some random numbers that I've given you. Let's take a look here. So inside of our framework that I gave you, right? Inside of the utility function, I have this thing which is kind of a mirror of what we see in Unity called random range, right? Where I have two numbers, a min and a max, right? Can we make this random range, work with vectors? How do we do that, right? So again, I want to take a look at this random range. Yeah, we can overload it just like we did last time. Let's go to definition here for the random range. So we have some minimum value plus some kind of float, right? Multiplied by a random number, right? Divided by some kind of random max, whatever the random max value is, right? And rand max is the maximum value that can be returned by random number functions, right? Divided by max minus min. So what this is going to do is going to go take your max minus min and multiply it by the maximum number. So usually it's 1, because usually random numbers go from 0 to 1. And these are pseudo-random numbers. Think about it, a table of numbers that we're basically choosing. And we're choosing a different part of the table depending on the seed, whatever the seed is, right? That's what's happening here. So what I want to do then is I want to use this random range to go from some vector to some other vector. I want to kind of generate a vector from some vector, some other vector. So what's that number going to be, right? Overloading. Yes, Nick actually has it right. It's what is overloading? It's different than overriding. Overriding and overloading. Overloading is names the functions are the same, as an example, but they have a different signature. So example, what we did earlier when we did our lerp, we have two lerp functions, right? They have the same name, but they return different things, and they have different parameters. They have a different signature, right? They have the same name, but it takes different things, right? And it returns different things. This is an example, a great example of an overloaded function, lerp. We want to do the same overloading function. We want to return a new GLM vec2, right? But what we want is instead, going back to that util, and go to definition for a second, I want another rand range, right? Let's make a new rand range. Okay, so static float, actually GLM vec2, if I can actually type properly. And we're going to make this random range from some GLM vec2 p0 to another GLM vec2, right, p1. And I want to have a number range between this number and this number. All right. So how do I code this thing now? If I was going to code it, so let's go to definition, right? Or let's navigate to create that. We'll create the declaration for it. Generate implementation. There we are. So we're going to use random range for this. Just like we did before, we're going to have a float number between min and max, where the min is p0 and the max is p1. All right, so again, I'm going to say some float, which is random x, which is equal to a random range of the p0.x and p1.x. That's the random number that I'm going to get. Some number between p0 and p1, right? And similarly, float random y is equal to random range of p0 dot y and p1 dot y. So some number random between these two values. And then what I'm going to do is I'm going to return a new GLM vec2 object that's between random x and random y. Okay. And now we can use resharper to fix this up. We're going to make const here, and we're going to use this to make const there. We're going to make also, we're going to return these ones as const and this one as const. We're also going to make this one auto, which is what it likes to do. I'm okay with that. It's also going to recommend that I rename this to random underscore x and random underscore y. Actually, I'm okay with that one. Random x and random y. I'm okay for this time around. So it kind of does this. And now we have no more warnings. And we have a number. If we have two, we take a vector and another vector, some range of vectors, and then we come up with the final vector. However, how do we use this function now in the future? How do I get from where I'm looking to where I want to look? How do I get this value, right? Some number between some value and another value, right? What I want to do is probably have some kind of wandering angle, okay? Some wandering angle. And I want to get the wandering angle from the left vector to the right angle, right vector somewhere in the middle, right? And I need an angle. I need a kind of an angle of attack from this one to this one. This doesn't quite do what we want it to do. This is just one part of the algorithm to do wandering, right? Why? Because the P0 vector is some degrees to the left of where I'm looking right now. And the P1 vector is some degrees to the right, let's say, as an example, of where I'm physically looking. So I'd have to write a new algorithm if I was going to write a wander algorithm where I have my current direction, I give it my current direction, and I give it an angle, right? And then I'm going to generate those two vectors from P0 and P1, then plug it into the random range to give me the new vector that I'm going to get, okay? Shouldn't you add a C prefix or something because it's a const? Yeah, I could if it was a member variable, but this is just something that's local. I'm okay with it. But Nikolai, very good, observation. Again, if it was something that I was going to do at the class level, yes. Okay, let's continue. So that is wander. Wander kind of wanders from one place to the other, and it does it slowly. It doesn't do the wander. Notice that kind of wanders a little bit more to the right, then a little bit more to the left, and a little bit more to the right, and it kind of meanders in a specific location. If you actually look at some of the wander algorithm here, it does wandering this way. Notice sometimes what it does is it uses almost like a kind of path following, where it kind of explores different directions. This is path following. This is wander. All right, so it kind of, here's the new destination, and it has some kind of range. This is like, let's say, the first vector, and this is the second vector. See this angle here between these two things? This is kind of like my wandering potential. I can wander from this point to this point, and this is the point that's been chosen, whatever that point is. But I'm going to choose a random number between here and here. Okay, and then wherever that is, I'm going to go in that direction for X number of frames. And then as soon as I finish wandering X number of frames, because we want to wait, we don't want to make it twitchy like it says here, maybe we'll walk for 10 frames or 20 frames or whatever it's going to be, then change again. We don't want to do this every frame. If we do it every frame, it'll look terrible, right? Okay, we're getting towards the end here. So that's wander, and that's the wander algorithm. It talks about how to do that. And then finally, we have some kind of random binomial. For me, what I've done is, instead of making a random binomial, I've used a random range. All right, still to do. We want to create some more SDL movement examples, and we may want to look at other 2D stuff that we're going to do today. This is the stuff we're going to do in lab. Okay, so we've come to the end of the lecture, and I've talked about a couple of things, just to review. One thing that we've talked about is movement in general. So how do we move? Kinematic movement. And the way we want to move is we want to normalize our motion. We want to get this idea of, so I'm going to go to the right place here. We want to get this normalized value from where we're looking. Where are we looking? Some normalized matrix. This is a matrix of x and y, right? Where we take to get normalized values of the target position, we take the difference between the target and the initial position, and we divide it by the magnitude of the of that line, of that vector. Once we have that, we have a normalized x and normalized y direction, right? That add up to 1. So these two things always add up to 1, x and y, all right? And then what we do is once we have that, that normalized direction, we multiply the normalized direction by the velocity in terms of how we're moving. But it's not enough to move laterally like that. We talked about, just as a review, we talked about how it's unnatural, right? How it's unnatural to move in a direction like so. We don't want to move like this to this. Instead, what we want to do is we want to move the path. We want to keep angling our path closer and closer. So as we move frame by frame, we move slowly, and we move in this kind of like, parabolic path, depending on our turn rate. That's something we also need to know about our object. How fast can it turn? The faster that it can turn, the smoother the arc, the lower the arc. The slower it turns, it might be a longer arc. So what I mean by that is, if I have a slow turn rate, maybe what I'm going to do is I'm going to kind of go out like this and then come back, kind of thing. As opposed to this arc, maybe it's going to be a lot less smooth like that. So there may be different turn rates that you will see different, kind of moving patterns from one place to the other. That'll create a different motion, right? Depending on the turn rate. The faster the turn rate, the flatter this line is going to be. If it's 100% fast, it's going to go directly from here to there, and it's going to look unnatural, all right? But we definitely want this to look where it's going, this look where it's going algorithm. So we talked about that in terms of smoothing direction. And we decided on making a lerping algorithm, right? So lerping, again, linear interpolation. We learned that what the t-value is. The t-value is that target number that we want to go to between 0 and 1. We want to remap all of our numbers between 0 and 1. Well, we want to do that, right? And once we've mapped between 0 and 1, we have control, right? Because we can relate all numbers. If I have any range, and if I remap all of my ranges between 0 and 1, I can compare them. That's the beautiful thing. It's all comparable, right? I can't compare 255 with 368 as an example. It doesn't make any sense. But I can say that from 0 to 255 is like saying from 0 to 1. And from 0 to 368 is from 0 to 1. And now I can map those two values so they mean something relative to each other. And we're going to see that later on this semester when we think about things like goal-oriented behavior, where I want to weight how much my behavior weighs over another behavior when I want to decide on my on what behavior the autonomous agents can take that particular turn, whatever that turn is. Okay, so pretty simple in terms of what we learned. Then we talked about, just as a review, we briefly talked about forces, and we looked at using the the formula to move from one to the other, P naught T plus V naught T plus 1/2 AT squared. That kind of idea, P naught plus V naught T plus 1/2 AT squared. And then we talked about simple steering behaviors. The seek is what we talked about first. Then we talked about flee, which is opposite of seek. And then finally, we talked about arrival and wander, right? Wander, we're not handling in our assignment, but seek, flee, and arrival is part of assignment number 1, okay? I also will share this paper with you guys, which includes many, many other examples, as well as flow fields, which are really neat, right? And a lot of other kinds of really cool behavior like flocking, which we're going to talk about next week, flocking, where there's separation and cohesion, stuff that we're going to look at next week. And this comes right from that white paper online, which is pretty cool. Notice that a lot of the more advanced behaviors have these little feeler lines in front of them. Think about this as a feeler that goes in front, and we can use these feeler lines for things like obstacle avoidance, where it's another steering behavior. I want to be able to avoid an obstacle. We're going to talk about that next week. Flow fields can be used like water flow. It can also be used to kind of direct a lot of agents in the same direction. If I want them to kind of follow a path around some kind of geometry, let's say, for example, around a hill or something like that, I can create these flow fields as invisible game objects that produce vectors for when another object goes into that area. It'll follow that, kind of the vector until it hits the next vector. Flow fields, kind of neat, yeah. So really cool direction mapping and stuff, which is really awesome. Okay, any questions around the stuff that we've talked about today? We're going to move. The next part is our next lab, if I'm not wrong, starts at 12. So from 12 to 2, and then we take a short break between 2 and 3, and then we go from 3 to 5. All right? Any questions? So that's it for me today. Thank you so much for watching. In this video, we talked about basic movement, kinematic movement, and some simple steering behaviors. And we'll talk more about how to code all this stuff within about 15 minutes when we start off our next video, which is going to be for the lab. Okay, so I'm going to stop recording this video here. And then when we meet again, we'll meet in about 13 minutes for our first lab, which is going to hit us at 12. All right, and then the next lab for us starts at 3. There's also going to be a lab 3 o'clock on the Friday. Guys, thank you so much for your attendance and attention, and I'll see you guys during the labs, or Alex will see you. Thank you so much, guys. I'm going to keep this channel open for people who are with me between 12 and 2. So for the other people that don't have to be here, I'll see you during the next lab or next week. Thanks so much, guys. Good luck on your assignment. Remember, assignment 1 is due very shortly. Thanks so much.